This is the magnetic field of a bar magnet lab. So the goals of this lab was to measure the magnetic field on axis and off axis and then compare it to the simulated magnetic field. These were the results that the net magnetic field increases as the distance decreases. And this was the magnetic dipole moment, calculated 1.0915 amperes times meter squared. And this was the measured off axis and simulated axis values. The magnetic field in Tesla relates to the current and distance between the source of observation. So this was the formula for the derivative of the magnetic field, and then if you have a loop, that's the formula there, and then for the dipole is there. So the dipole is calculated by the current times the loop area, and the direction of on-axis is the same direction of the magnetic dipole moment. But if you are perpendicular, it's half the magnitude in opposite direction. This is the magnetic field of a bar with the constant K, which is a combination of magnetic constant, and then this is the general formula for a magnetic field of a magnetic dipole. So this was a visualization of the magnetic field, so you can see in the perpendicular, it's going the opposite way. System was the observation point and the surroundings was the bar magnet. So this was the procedure used for the lab, and then this was the experimental data, and you can see the equation of the line here was used in this formula to get the constant K and calculate the dipole moment here. So these were the observations from the lab that as the distance decreases, you can see here the measured x component of the magnetic field increases. And these were the computational constants put in from the mu moment 1.0915, and then this was the scaling of the arrows. This was the off-axis magnetic field and magnetic field arrow in the computational model, and then these are my results. So the arrows here drawn may be a little off, but these were the results from the magnetic field simulation. This is the discussion for the magnetic field. As the distance between the magnetometer and magnet decreases, the magnitude of the magnetic field increases. And you can see here with these values, the magnetic dipole moment was 1.095 amperes times meter squared, and then this was the experimental magnitude of the magnetic field here and the simulated magnetic field. So the percent error was quite big due to these reasons that there were a lot of other sources of magnetic fields distorting the measurements and inconsistent placement of the phone, which could lead to slight movements. The surface inconsistency, it was not flat completely, and the measurement error with the magnetometer since it was an app on the phone, and then the measurement error between the distance between the magnetometer and the magnet could have been off. So what if you had not oriented the experiment to compensate for magnetic north? The x components and the y components would change because the phone was definitely probably on an angle because you can't be completely sure, but the z component would not change because it's on a flat table basically. And then what if you were to stick two identical magnets together end to end? The magnetic fields would combine, and I expect that they would double, but I'm not completely sure. I'd have to test it experimentally. And then the measured distances would decrease since they're proportional.